Hi there, chemistry team, chemistry coach coming at you with my nice Father's Day shirts. Gotta love these things. Oh, kids are awesome. All right, a little introduction to titrations. So, this is going to be video number 5 on our chapter. We already covered buffer solutions, and we covered the common ion effect. So, what we're going to be doing and if you're a little rusty on those, review those first 4 videos on this chapter on acids and bases and titrations because we need to comprehend and understand how buffers are created and how to figure out the pH of buffers, Henderson-Hasselbalch equation, all that fun stuff. And we need to understand the common ion effect. So when we are doing titration, so this is just a messy board here with a little review from last semester on what a titration is, which I'm assuming all of you did titrations in introductory chemistry or first semester general chemistry, where you're just taking an acid and neutralizing it with a base using a burette. So we'll review that just briefly. You know, get the common language back, blow some dust out of the brain, get you going again. But we're going to take it to a whole nother level. And what we're going to be doing is calculating how the pH changes from the beginning before the titration begins all the way to where the color changes. Remember, oh, look at the pretty pink color from the phenolphthalein. Oh, it's too pink. Now I got to back titrate. You remember all that fun stuff in the lab. But we're going to start, what's the pH in the beginning before we add any titrant to our solution. And then we're going to take it all the way through to where the indicator changes color and all the way past that. And we're going to be able to calculate. I know you're so excited about this because in lab we just did it till it turned pink and we're done. But we're going to go way beyond that and look at it piece by piece. Kind of like a time frame photography. What's the pH here? What's the pH here? What's the pH here? If I squirt a little more in, what's the pH here? So let's go review a little intro and review to titrations here. All right. So we've got our Erlenmeyer flask. Commonly, you'll have some unknown acid solution in there with a few drops of an indicator. We'll talk, review what the indicator is for. It doesn't have to be the acid. There could be the base, but typically you'll see the acid of some known volume and usually some unknown concentration. All right. In the burette itself, we'll put the base. And commonly that has a known concentration. It's a standardized base. You could have an unknown base and a known acid, or an unknown acid and a known base. It doesn't matter. It doesn't matter. But typically the base will go in the burette. And we call that the titrant, what we're adding from the burette into the Erlenmeyer flask. And we want to use that Erlenmeyer flask because it has that smaller entrance hole to reduce splashing. So you want the tip, there's a little glass pipette tip here. You want that slightly inside. So I like to lift, I like to dispense the liquid with my left hand and lift the Erlenmeyer flask up a little bit and swirl it while I'm doing it. You can look at videos of titrations because I don't want to lose any drops on the outside of that. You're toast if that happens. But I don't want that clanking on the inside either, so I'll swirl it around, and then when I'm done, I'll tab off the drop and spray that down with some, because you can spray this down with DI water. It doesn't change the number of moles or equivalents of acid or base, right? So that doesn't really matter. So we'll start. We use, obviously at our college, Mohr burettes, MOHR, which has that little, you got the glass burette with a plastic tubing here with a little glass bead in the middle, and then a little plastic pipette, a glass pipette tip at the bottom. And so all you do is you just pinch the plastic on the side of the bead and stretch it, right? You stretch the plastic on the side of the bead, it creates a little air gap, and the liquid comes through. And you can really control that rate very, very precisely to the point where I can get to that color change with a quarter drop or less. Tap it off inside the flask, spray it down. Sweet. So we're going to fill up our burette to some initial volume here. And we're just going to drain it down until we hit the color that we're after. Record that final volume. Because remember, a burette is just a volume transfer device. It's a way to transfer solution of variable amounts. We don't really care where we start. We don't care where we end. So I just start somewhere up towards 0 and make sure you end before the 50 line. It usually goes from 0 to 50. Don't go below the 50 line of your toast, and you can't start above 0. So record your initial with your burette reading card, record your final, and then just subtract them. So the amount of volume that was dispensed is the final minus the initial. And that's why you have a bigger number on the bottom and a smaller on the top. So it seems upside down to you, but you have to do it, otherwise you get a negative volume dispense. That doesn't make any sense. So review lab techniques for that. But these are the two theoretical terms we need to remember, right? The equivalence point is when the acid and the base neutralize each other exactly. And we do that based on equivalence rather than moles. It's not called the mole point, it's called the equivalence point. So if I had, and if you're rusty on your equivalence, go review that. So if I had, say, 0.2 equivalents of acid, it would require 0.2 equivalents of base to neutralize it. It's always a 1-to-1 ratio, regardless of the identity of the acid or base. Not necessarily true with mole to moles. If I have 0.2 moles of acid, it may or may not require 0.2 moles of base. It depends on the stoichiometry of the neutralization reaction. But when you're dealing with equivalents, it's always 1-to-1. So the number of equivalents of acid requires the exact same number of equivalents of base. Once we've done that, if I have 0.2 equivalents of acid and I've added 0.2 equivalents of base, boom, that's the equivalence point. They've exactly neutralized. Right? So if I just start with acid, I'm going to have a pH less than 7, right? And as I start adding base, that pH is going to start increasing, right? But as long as I have more acid than base, it's still going to remain acidic. And then we add the indicator to that. We tend to use phenolphthalein, but I'm going to go through a video just on indicators. There's a lot of cool indicators. But phenolphthalein is a good one because it goes from colorless in acid solution to pink and basic. So it's always easiest for our pathetic human eyeballs to see a colorless to a color rather than a color to another color. It's just easier to go colorless to a color because we don't care what the color is. It's just that it's not colorless. It just happens to be pink, so we can find that get a nice white background, have your flask in there compared to like a flask of tap water, so you have a colorless reference. You just get that faintest pink color possible. So the end point is when the indicator changes color, because the base is clear and colorless and the acid is clear and colorless. You have no idea where the equivalence point is. Our pathetic human eyeballs can't see that. But we can add an indicator that changes color at that point. So the indicator chosen must have its color change, its endpoint, trigger when the equivalence point is reached. Right? Again, we can't see it, but we can't see that, but we can see the color change, the endpoint. But as we're going to find out at the higher level here in second semester general chemistry, there's lots of different kinds of titrations, and some indicators don't work that you would think. Phenolphthalein might not be the best indicator for some titrations. It's just we've always used it for the classes we've done because we've done simple titrations. All right. So pretty key factor there. So swirly, 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 get the faintest pink color possible. And if you go past the end point, there's an option in lab where you can back titrate it, go add some more acid, turn it colorless again, and then add some more base, and you can go back and forth until you get the faintest color change possible. It complicates the mathematics and calculations a little bit, but makes it so it's almost impossible to screw this up. It's a wonderful situation. All right, so just remember the equivalents are the same. We start with an acid, assuming in this scenario, pH less than 7, we're adding base. As long as there's more acid than base, the pH is still less than 7, right? Let's say we have a strong acid, strong base, and let's say they neutralize it at pH 7. That'll be one of our scenarios. So the pH increases as I keep adding base, and then at pH 7, we hit the equivalence point. The indicator changes color. We have a true neutral solution at pH 7, right? It's still going to be colorless, all right, because of that particular indicator if it's phenolphthalein. So we need to add a tiniest portion of this base titrant to make it as barely basic pH above 7 as possible in this scenario, right? I'm oversimplifying things here. And once we do that, then it turns pink when it's just that slightly basic color. And so we're actually adding a little bit of excess base. That's why you want the faintest pink color with just the tiniest portion of base beyond that equivalence point to hit that. And then if I keep adding base, then the pH will it's above 7, and we'll keep going all the way up to where, as long as I have more base than acid, it'll be basic. If I have more acid than base, it'll be acidic. Right? You get the deal. So let's take a look. Let me get rid of this, and let's introduce you to the types of titrations we're going to look at. We have 4 or 5 different scenarios. And then what I'll do is I'll do a different video for each one of those because they're slightly different. We need different indicators. The pH at the equivalence point will be different for different types of acids and bases. So let me write those up on the board here for you. All right, so quick introduction to the types of titrations we can run into and what we tend to focus on in the lab. So 5 basic kinds. If you look at it's not many combinations. You got acid and base. But what makes it more than just one combination, acid and base, is the acid strong or weak, and is the base strong or weak? Remember, strong acids and bases, right? If you got a strong acid or base, that reaction is going to go to completion. Super reactive. If it's weak, ooh, we got a problem here. So typically what you'll see in introductory chemistry and first semester general chemistry, most of the time, but not always, you'll get a strong acid titrated by a strong base. Typically the strong base, and this is your titrant, that's what's coming out of the burette. That's typically going to be a known solution of sodium hydroxide, right? A standardized solution with a known concentration. And then the strong acid is probably going to be hydrochloric acid or nitric acid or something like that. No big deal. And we'll find that for each of these, the pH at the equivalence point will be a little bit different. So we're going to have to look at them each in turn and then find an indicator, because an indicator that works for the first type might not work for the second or third type, right? It may or may not. We have to check and look at it, because when the indicator changes color, that will happen at a specific pH. And the equivalence point will happen at a specific pH. We want those to match, right? If they don't match, then your indicator's not going to work, and then you'll miss the equivalence point because it'll turn color at the wrong time, either before or after the equivalence point. That's not good. Sometimes you will see this as well in introductory or first semester of general chemistry, a weak acid, right? So maybe acetic acid and vinegar, or some weak acid like that, with a strong base, typically sodium hydroxide. Right? Since these have a strong speed, as long as one of the two are strong or both, that will drive towards completion. So that's why in lab, you always want typically your titrant, if it's a base, to be sodium hydroxide. You want it, one, it's cheap and plentiful, and two, it drives to completion. We want that to be able to do the calculations. So say we have an unknown concentration of a strong or weak acid. Well, if we know the volume of them, and we know the volume and concentration of the strong base added, very easy to calculate the concentration of the unknown acid. Or vice versa, if we know the acids and not the base concentration, as long as we know the two volumes and one of the concentrations, we can solve for the other concentration. Very easy. Well, the third one we'll run into is, what if you have a weak base and a strong acid? All right, that's not one you're probably going to run into in first semester general chemistry or prep chem, introductory chem, because the weak base would have to be like ammonia or an ammonia derivative, some kind of organic amine. Not as fun to work with, maybe to an organic chemist, but ammonia, like making an ammonia solution, not pleasant. So usually those are the only two you've probably run into at this point in time, would be my guess. But we'll look at each of these. Now, if you have a weak acid plus a strong base, that pH at the equivalence point will be slightly different than the pH here. So what we need to do is take what we've learned and analyze what exists at the equivalence point. What species are there after the acid and base neutralize? What happens here when you have a weak acid and a strong base? When they exactly neutralize each other at the equivalence point, you won't have the acid or base left. What are the products of that neutralization reaction? What is left? And they're going to go to completion. Right? This one will go to completion, weak base plus strong acid. But again, harder. It's more technically challenged, I think, in a laboratory environment. So theoretically, we can play around with it, which we will, but we probably won't do that in a laboratory environment. Number 4, you may have seen, possibly, up to this point, a polyprotic weak acid. All of these are monoprotic with one acidic hydrogen, HCl, HNO3, those kinds of things. A polyprotic one would be like H2SO4 or oxalic acid, H2C2O4. It's got 2 acidic hydrogens. Well, as long as you're reacting it with a strong base, it's still going to drive to completion. So you could figure out the concentration of that pretty easily. But we're going to be doing titration curves and tracking how the pH changes over time. That's going to be a lot more complicated because it goes in steps, right? So you'll hit that first equivalence point where it neutralizes the first acidic hydrogen on the acid. And then you'll get a second equivalence point when we see these curves where it neutralizes the second acidic hydrogen. Not so much fun to do or look at theoretically. So we'll briefly poke at those, but at this class, we're not going to be doing those in lab or anything. Now, last one. Now, all four of those, since you see a strong species there, those will go to completion, regardless of their identities. But what if we have a weak acid with a weak base? Oh, man. That means it's not going to drive to completion. Good luck with the calculations on that one, right? You can't do that in first semester general chemistry or intro chem because they haven't really looked at equilibrium like you do in second semester general chemistry. So it's possible, but it would be highly unpleasant to do. And we don't do that in lab because it doesn't run to completion. So we are not going to cover that in this class. We have time limits. It's just not necessary for us. So we'll cover mostly the first three with a focus on the first two. We'll talk about number 4 with titrating polyprotic acids. And I might talk about this a little bit, but we're not going to go into gory detail on it. So that's in essence what we're going to do. So in the next video, I'm going to put up titration curves and what those look like between these different types of titrations, and then some indicators. And we're just going to do an overview, and then we'll get into some crazy calculations. So throughout all of this class, some of the, I wouldn't say challenging, but most tedious types of calculation come from titration. What's the pH at different points along the titration? Are we before the equivalence point, after the equivalence point? They can get pretty crazy. But if you know what you're doing, you just walk your way through it. But it might take a whole page of calculations for some of these. Yay! There's no new concepts here whatsoever. We're taking everything we've learned before and just applying it to this. All right, let me put the next video up.